Welcome to Monty Hall. This is the Quantum Cryptography Talk. If you're in Monty Hall for the Quantum Cryptography Talk, you're in the right place. Otherwise, this is the time to get up and walk somewhere else. The gentlemen that we have here with us tonight, we have Ilya Gerhard, we have Vadim Makarov. Vadim is with the Norwegian University of Science and Technology. Ilya is with Center for Quantum Technologies in Singapore. They're going to talk about quantum cryptography and why it is absolutely something that you want to know about. And here they are.
Okay, can you hear me? It's okay? Fine. So today we are going to present you results of recent experimental work which we have done just last month. Can you hear me well? Okay? This experimental work done last month is a joint collaboration of two folks, Vadim Makarov and Chin Liu from the Norwegian University of Science and Technology, Trondheim, and Ilya Gerhard, Antje Lamas-Linares, and Christian Kurtziefer from the Center for Quantum Technologies, Singapore. My name is Vadim Makarov, and part of the talks will be presented by Ilya Gerhard. The outline of today is a general introduction into quantum cryptography. Then, after that, we will present the particular quantum crypto system which we are going to crack. After that, we describe the vulnerability which is going to be used for cracking this quantum crypto system, and present a complete description of the attack. After that, Ilya Gerhard will talk about implications of this attack for other quantum optics experiments. Quantum cryptography, the original idea of quantum cryptography, you can say, originated in the mind of Stefan Wissner around 1970. He proposed to use money physically impossible to counterfeit by encoding a serial number of the banknote on a sequence of spins stored in the banknote. Completely impractical technology, still impossible to implement, but a physically sound idea. He tried to publish it, and of course the paper was promptly rejected by the journal, so it was never published. But in 1984, Bennett and Brassard, who know about Wissner's idea, took it into a much more practical form. They proposed to do secure communication by encoding secret bits into a sequence of photon polarizations. And now it was instantly much more valuable idea because it was implementable. You can send photons down optical fiber or free space optical channel, and you can make this idea work with the current technology. 5 years later, they built a proof of the principle experiment, a quantum key distribution system that worked at over 30 centimeters above an optical table. And from that point on, people believed that it's going to work, and the field started to develop exponentially. The number of papers increased every year, and I think this process still continues. Very quickly, people built fiber optic quantum key transmission links, first over 1 kilometer, then very quickly over 20 kilometers. It took 15 years for the field to mature to the first commercial quantum crypto systems. The current distance records is 200 kilometers transmission demonstrated on fiber and 144 kilometers in free space. I think that this year record is actually 250 kilometers. 200 was just 2 years ago. And to put this talk into perspective, we also plot our achievement in this timeline. So, what does quantum cryptography do? What problem it solves? This is a standard symmetric cipher encryption scheme widely used everywhere. In this scheme, we have two communicating parties, the sender Alice and receiver Bob. Before Alice and Bob can start communication, Alice distributes to Bob a secret random key through a secure distribution channel. After Alice and Bob both have a copy of this secret key and they are sure that nobody else knows the secret key, they can use classical symmetric ciphers such as, for example, AES or DES to encode a message to be transmitted and transmit them over an insecure public channel, for example, internet, in an encrypted form. And then the same key is used to decode the message into the original clear text form. The problem with this scheme is the problem of key distribution. How do you distribute the secret key so that nobody eavesdrops? Two methods are used currently today. One method is distribution by couriers, used for the most secure communication, like diplomatic channels, spies, and so on. The other method is public key cryptography, which relies on mathematical assumptions, unproven mathematical assumptions, one-way functions, to distribute secret key from Alice and Bob. The problem with the first method is that courier distribution is expensive and inconvenient. The problem with public key cryptography is that it's not proven. We don't know if it's secure. It can be broken overnight by a sudden mathematical advance. If somebody finds how to factorize large integers, your public key cryptography is toast immediately. And actually, we know it's in fact broken on a quantum computer. We know an efficient factorization algorithm for a quantum computer. So as soon as the quantum computer is built, public key cryptography is toast. And here, quantum cryptography comes to the rescue. It proposes to distribute a secret key from Alice to Bob through an open channel by encoding it on a sequence of quantum states, for example, polarization states of photons. This is something which is not possible in the classical world, but possible in the quantum world. So this key distribution channel can be open to eavesdropping. Anybody can try to eavesdrop on the sequence of quantum states, but quantum mechanics guarantees that any attempt of eavesdropping will be guaranteedly revealed. So let's see how Alice can distribute to Bob a secret random key over an open channel. Alice prepares a sequence of single photons, preparing each photon in a randomly chosen one of the four polarization states, vertical, horizontal, or two diagonal polarization states. Those four polarization states are grouped into two bases, vertical, horizontal bases, and diagonal bases, and each of them in each basis is assigned a 1 and 0 bit value, which represent the random key bit values. She sends photons over to Bob. Bob, for each photon that comes to him, he randomly and independently of Alice chooses one of the two detection bases, vertical, horizontal basis, or the diagonal detection basis. Bob detects the photon and records his detection result, as well as his basis choice. After Alice sends to Bob a number of photons, for example, 1,000 photons, they stop communication and communicate over a classical channel like internet between Alice and Bob. They compare their basis choice, but not the bit values. In about 50% of the cases, Bob will have randomly chosen the basis, not the same basis as Alice. For example, Alice chosen this basis for encoding, and Bob chosen diagonal basis for encoding. In this basis, Bob's detection result is completely random, 50-50 probability to detect either polarization, and those bits are discarded from the key. In the remaining half of the cases, Alice and Bob have chosen the same encoding basis, and they have the same bit values. Those bits are retained and form a secret key. Now, what happens if somebody tries to eavesdrop on this transmission? The eavesdropper, commonly called Eve, she does not know, at the time of transmission, she does not know in what basis Alice has encoded the photon. So she has to choose the basis randomly. And then she has to regenerate this photon and send it over to Bob, so Bob can detect it and record the bit value. So the best she can do again is to regenerate the photon in the quantum state she has detected. But in half of the cases, if we'll choose a wrong polarization basis and get a random bit value, she regenerates this photon and sends it over to Bob. And Bob often happens to choose the proper basis and detect this photon detected by if in a wrong basis, in the proper basis. And then he gets 50% of errors in this detection event. So this will introduce errors between Alice and Bob in the final retained bit sequence. Alice and Bob check for eavesdropping by revealing a random subset of this bit sequence and comparing it between them. If they see errors, this signals that there has been eavesdropping. Then they don't pass this key to a secure application. They can start over or sound an alarm. They only pass this bit sequence to a secure application if there are no errors in it. Quantum cryptography has been successfully commercialized for several years. There are at least 3 commercial companies where you can buy such systems. A typical commercial system consists of 2 parts. One part is the quantum key generator, which generates this random secure key. And another part is classical virtual private network high-speed encryptor, which uses this key from the quantum unit. And this encryptor runs a high-throughput classical cipher, AES, and all 3 systems which you can buy. The unimproved security is achieved by updating the AES cipher key several times a second. They say that this makes AES harder to crack. And for more secure applications, there's also an option to use this quantum-generated secret key as one-time pad. But of course, then the problem is the key generation rate is quite low. You can only use this one-time pad encryption for short pieces of the most sensitive communication, like text messages or maybe a phone conversation encrypted by one-time pad. For the time being, the systems are quite expensive. Point-to-point link will cost you about 100,000 euro to install, or maybe a bit less if you bargain. So what is our motivation for this experimental work which we have done? We decided to look. The last few years, it has been a big question. How secure quantum key distribution systems are in practice? Especially that now they are beginning to be used commercially. The situation with security is such that we have very strict security proofs based on quantum mechanics, which prove that quantum cryptography is unconditionally secure or absolutely secure if you want. But those proofs assume a certain idealized model of the communication equipment. Unfortunately, the model of communication equipment assumed in the security proofs is not exactly what you have in actual hardware implementations. In hardware, there are many loopholes, and there are many properties of the electro-optical components of which the systems are built, which can be used for eavesdropping, if you look closely. We know several of them, and so far only such vulnerabilities have been discovered, but nobody built a full exploit. So our motivation for this attack to demonstrate that it is actually possible to build a complete working exploit, complete working eavesdropper using one of the loopholes. Now I pass over to Ilya Gerhardt, who will present the particular quantum key distribution system which we are going to attack.
Okay, hi. So actually, I'm not the online shop, but still, we have a quantum key distribution system in Singapore. So you do not have to click on the online shop to buy this 100,000 euro thing, and you basically can have a collaboration with us to use our system to try to hack it. So our system is a specific system, and this is a system I now present. And this is a specific system which is, I think the attack which is introduced in this talk is not only attacking our specific system, it's basically attacking a certain style of single photon detectors. So our system has a certain property which is called entanglement based. So it's based on entanglement, and so we have a source of entangled photons. And the first question which arises is automatically clear: what is entanglement? This is some funny quantum property, and I try to give my best to explain it the whole day over there in the bike shed to everybody who really tries to understand it. And also I will introduce a little bit how this entanglement can be used for QKD and what is interesting about this entanglement-based protocols. And I don't think I covered it, but I will eventually comment a little bit what spells inequality. So let's have a look on the system, and let's have a look on the basic fundamental principle. So in quantum mechanics, you can have a thing. Let's say you can write down an equation, and you can formulate a quantum state, which is not distributed only, which I cannot only hold in my single hand, but which can be a joint quantum state between two things. And for example, I have a source of entanglement, so this is labeled as S here, and this source of entanglement can send out, for example, photons or atoms or whatever things can be entangled. And then we have two stations, 1 and 2, and they can make a measurement. And this funny thing of entanglement says, if I have a certain outcome in 1, I know if I make a certain measurement in 2, what the outcome will be. So in 1935, Einstein, Podolsky, and Rosen came up with the idea, and they said, hey, this is a little bit funny. So I measure something in 1, and eventually 2 light years away over there in the other galaxy, there's another measurement which I know the outcome in the moment I measured 1. So is it a kind of spooky action as a distance? This was basically the kind of saying. So okay, let's have a look how we write down this state. So I just wrote down one of the states. It's so-called phi minus state. And again, I just summarize exactly what I just said. And here's the laser pointer. So if I measure in my measurement station 1, if I measure a photon which is up, down, let's say vertical, I measure in 2 automatically a horizontal photon. Or I can measure in 1 the horizontal photon, and in 2 I measure the vertical photon. Let's say this is I would say, a pretty classical correlation. So you can just send a vertical photon over there, a horizontal photon over there. Fair enough. The interesting point, what really makes it a little bit spooky, is if you make a measurement in a different basis, basically, for example, in a basis where you look on photons which are not horizontal and vertical, but minus 45 and 45, if I measure 1 to be 45 degrees, the other one will be minus 45 degrees. So it's always the kind of perfect anti-correlation. I always get the opposite 90 degrees turnaround polarization. So this is a little bit funny. So this is this action at a distance, which was formulated by Einstein, Podolsky, and Rosen. So this is basically the kind of first description, and so it's also called an EPR source, a source of entanglement, a source of entangled photons, for example. Photons are pretty convenient to work with because you can transfer them. So entangled atoms, it's a pain in the neck. You have to carry it in a vacuum chamber, and so it's not really at a distance, I would say. And in 1964, John Bell came up with a nice measure for this non-locality, this kind of funny action at a distance. And this is the underlying principle, or let's say this is a little bit like a security proof of all what comes now. So let's be a bit more technical here. So we have the source. We send out for example, photons to a polarizing beam splitter. This basically tells you if it was horizontal and vertical. If I have a measurement in this output port 1 here, I have a output also, or I make the second measurement here. Perfect anticorrelation, for example, H and V, V and H. So I always have this opposite one. So the interesting point comes in the moment I do not only this H and V basic measurements, I always turn the bases in between. So let's say what Vadim explained is a pretty straightforward way to explain quantum cryptography. This is a protocol which was developed in the 80s, 1984 exactly. BB84 is the name of the protocol. And there you need a lot of random numbers. So you really kind of, Alice sends over a photon in a certain polarization state, in a certain basis, so randomly choosing the bit, randomly choosing the basis, over to Bob, and Bob measures again in a random chosen basis. So this is the idea. So you need, first of all, a lot of random numbers. So you need, I would say, three times the random numbers of bits actually sent over. So there's no, it's not a good idea to reuse random numbers or something like this. You need 3 random number generators, which are, if to get highest security, have to be true random number generators. So the entanglement-based stuff basically uses just a beam splitter, and it's, if there's a single photon coming into the beam splitter, 50-50 beam splitter, there's no polarization or whatever, it just, the photon chooses 50-50 chance to go through or to be reflected. That's just probability. The other option, or the other really big advantage of these entanglement-based protocols is nobody tells you in the first protocol, Alice is sending a photon, that you have a photon, let's say if we have these 4 states, I again revise this, it's let's say vertical, horizontal, minus 45, plus 45. It could be that these are 4 photons from 4, for example, very dim light sources, just 4 dimmed lasers, and they are just blue, green, red, and yellow. So an eavesdropper just measures the color of light and knows exactly what to resend. So, but the interesting point about the entanglement-based protocols is that you can determine the dimensionality of the Hilbert space, this is how the nerds call it, to judge how much knowledge is in the hands of the eavesdropper. So basically with this entanglement, so you always measure the quantum state of light, and then you know later on, okay, an eavesdropper knows so and so much. This is at least the idea. So let's have a look on the system. As I told you, we have this funny source of entanglement. It's pretty straightforward. I'm going to show you a picture in a minute. So basically we have a Slaughter Blu-ray disc recorder. We focus it into a so-called BBO crystal. This is some fancy chemical crystal. And then of one single blue photon, 2 red photons, 2 red entangled photons are coming out. One is directly measured here in a kind of polarization analyzer. And then the other one is sent over, for example, in a single mode fiber to the other station of our quantum key distribution setup. And the whole system, the whole polarization state is measured again here. And here again, here we have the random number generator. So basically the photon goes over, let's say a few meters, then it goes in here. And here the entrance beam splitter of our detector determines if it's measured in the horizontal vertical basis or in the plus minus 45. So if it's just reflected, here we have a polarizing beam splitter, horizontal and vertical. If it's transmitted, the basis is turned by 45 degrees, and then we have the polarizing beam splitter to determine if this was this or that. So, and later on, we basically take down the arrival time of the photons, because the photons which are generated in this BBO crystal, they are pretty nicely correlated. We talk just over a classical channel, hey, Bob, when have you detected such a photon or a photon? And Bob says, yes, I have detected at so and so much time a photon, and I measured in such and such basis. And Alice says, cool, I basically measured something in the same basis, or in a kind of corresponding basis. And then they can correlate the outcome of the 2 measurements, because we know if we make a measurement here and the outcome was H, the outcome will be V here. So horizontal and vertical. Let's have a look on the source. The source, as I told you, it's a Slaughter Blu-ray disc recorder. So you see it a little bit from the side here. Basically, this is the housing for the diode. A little bit of focusing optics and a little bit of fiber optics as well. And then it basically is transferred through the breadboard into a nonlinear crystal here. The 2 photons are just captured by 2 mirrors, and then they are kind of freed into single mode fibers, one here and one up there. So these are the entangled photons, which are used later on for the quantum key distribution. So they are temporally correlated, as I said, and they are broader than a dimmed laser. But I think this is something which is really technical. But I think if you come over to the bike shed, I will introduce all the concepts on these pair sources. So the detection again is basically the photons come in, they go to this 50-50 beam splitter, 50-50 chance to go over here to measure in H and V, 50-50 chance again to be transmitted through a half wave plate and to measure in plus and minus 45 degrees. So the real unit, and you can really have a look at the bike shed, I brought it along from Singapore, is this one. So you see the 50-50 beam splitter and the polarization beam splitters, which are in there. It's pretty, let's say, it's still a macroscopic device. So I think this is basically the talk, or the kind of part where I introduce the system. But now let's look more in detail onto the single photon detectors, because they are not perfect, and I think Vadim will walk you through the imperfections of single photon detectors. Thank you.
I would like to focus on those little devices they have in their polarization units, because those are avalanche photodiodes, which are connected to a detection electronics. And this is the component of the system where we have a loophole, which we are going to exploit. Let's look at the response of this particular detector type, passively quenched single photon detector. An ideal single photon detector will have linear response. When there is absolutely no light coming, there are no output counts. And when you increase the input intensity of light, the number of counts increases linearly, up to infinity, ideally. A real detector differs in two aspects. First, in the absence of light, it still gives off some thermal counts, called dark count rate. But this is not a loophole. This is not a problem for security. Then, as you increase the intensity of light, the output count rate grows at first linearly, but then it saturates, decreases, and at a certain light intensity drops to exactly zero. The detector is blinded by the incoming light. This is a loophole. This light intensity at which it's blinded, it's not very high. It's tenths of picowatts, actually. Certainly less than a nanowatt. Let's see why this happens. This is an electrical circuit of a passively quenched single photon detector. We have the avalanche photodiode, which detects the incoming photons. The avalanche photodiode is reverse biased at several volts above its breakdown voltage from a high voltage power supply through a large resistor. When there is no photon coming, the current through the avalanche photodiode is exactly zero. No carriers in the photodiode, no current. So, and then we have an important element in the scheme, two stray capacitances, very small capacitances. They are not actual capacitors. This is just a stray capacitance of the APD, and this is stray capacitance between this node and the ground, each on the order of 1-2 picofarads. They are important because when there is no current through the APD, those two capacitances are charged to exactly the bias voltage, which is 10-15 volts above the breakdown voltage of the APD. When there is a photon coming to the APD, it causes a formation of an electron-hole pair in the junction. And this single electron-hole pair quickly amplifies, multiplies through the avalanche process, and leads to a very large number of electron-hole pairs and a macroscopical current pulse through the APD, which is converted to voltage at this resistor and comes to a comparator and forms an electrical output pulse at the output of the detector. The capacitances are small, so they are quickly discharged in the avalanche process in about 1-2 nanoseconds, and the voltage at the APD drops below breakdown. Then the avalanche quenches. It stops again. Again, zero current through the APD. Then after that, those capacitances are slowly discharged through this large value resistor with a time constant of about 1 microsecond, back to the original value, 10-15 volts above breakdown. During the recharge time, for a time about 1 microsecond, the detector remains completely insensitive to incoming photons. because the voltage on the detector does not reach a value at which it could have an avalanche with a sufficient magnitude to trigger the comparator. Normally, it would recover. But what happens if after this first photon, they continue coming photons at a certain rate? When you eliminate the detector with several tens of picowatts in continuous elimination. Each photon causes a small avalanche and resets the voltage of the detector all the time to the original value below breakdown. And those avalanches are small, they don't cause comparator flips. So the detector remains blinded and completely insensitive to single photons. It also doesn't have any dark counts. But in this regime, the avalanche photodiode still remains a photodiode. It will still have a photocurrent if you apply a bright pulse of several milliwatts amplitude at this point. So it can still produce sufficiently large current to cause a detector click if you apply a sufficiently bright pulse here. And then whether it produces the click or not, whether it crosses the comparator threshold or not, depends on the classical amplitude, classical power of this bright light pulse. So the detector now becomes working in a classical mode with a classical sensitivity threshold. We can exploit this. We have a choice. Now we have a choice of two control intensity diagrams. One option is to keep the illumination of the detector at least the blinding intensity level, in which case it's blinded and you never have a click at the output. Another option is to superimpose this bright pulse at the background illumination, and then the detector gives off a single click, and we call this intensity diagram a faked state, as opposed to a true quantum state. Now, we know how to control a single detector, but we need to control not just one detector, but we need to control a complete Bob's polarization analyzer unit with 4 such detectors and polarization splitting optics in front of them. How do we do that? Actually, we attack the whole system. To crack the system, we use an intercept resent attack. In an intercept resent attack, if sits in between Alice and Bob. If has a replica of Bob's detection setup, and she actually detects all the photons which are coming down the transmission line from Alice. Then, from my introduction, you know that the attempt to regenerate the detected quantum state in a straightforward way is destined to fail, because if she tries to regenerate a vertically polarized photon, sends it over to Bob, it will register as errors in Bob. So this straightforward attack is destined to fail. Instead, if forms a control diagram of the type which were on the previous slide, to cause a click always in exactly the same detector as she had a click in, she targets exactly the same detector and 0 click probability in the other 3. So for example, when she detected a click in the vertical polarized detector, she needs to cause a click in this one. She sends background illumination to blind all 4 detectors. The background illumination has circular polarization and is split evenly 25% all 4 detectors, and the intensity is sufficient to blind all them. Then she superimposes a vertically polarized bright light pulse. This vertically polarized bright light pulse is split evenly, half by half on this input beam splitter. In this polarizing beam splitter, almost the entire intensity goes to the vertical detector, and the intensity of this pulse is chosen such that it's just above the detector sensitivity threshold, so it causes a click in this detector. This detector gets practically nothing, and those 2 detectors get half the intensity of this detector. And we choose the intensity such that this half the intensity is below the sensitivity threshold, so they don't give clicks either. This is how the attack works. Well, perhaps to understand, you note that now it's not Bob who actually detects the single photons, but it's Eve who uses a replica of Bob's detection apparatus to detect single photons, and then she just tells Bob to make the click in the same detector. So Alice and Bob are thinking that Bob is detecting single photons, while in fact the detection unit is now belongs to Eve, and Eve knows everything about the transmitted photons, and of course can know the full quantum cryptography key. This is more in detail. Okay, this is already presented by Ilya. This is their QKD system with EPR source and polarization analyzer in Alice, and Bob, which consists of polarization analyzer, and a transmission line between them. Now to cause 4 clicks in 4 different detectors, we need 5 lasers in Eve. This is Eve. She has a copy of Bob's setup. Then she has 1 laser, which produces so-called polarization to blind all 4 detectors in Bob. And then she has a pulse generator, which, depending on which detection results Eve had, forms a pulse in one of the 4 lasers. Each of them is aligned to a particular polarization to target one of the 4 Bob's detectors. They are combined, and this faked state is sent to Bob. We tested this attack in a lab and then went out to the campus of the National University of Singapore and installed, first we installed a quantum key distribution system. We laid 290 meters of fiber through 4 buildings on the campus, single mode fiber. Then we installed Alice at the building of the Center of Quantum Technologies. And we installed Bob at the building of, in the office of the physics department. And down the way, the communication went through the mathematics department. Here you can see in Alice's setup the entangled pair source with laser on, blue laser on. You can see Alice's polarization analyzer and Alice's rubidium clock, which provides time reference for a timestamp unit. In Bob, you can see Bob's polarization analyzer unit with 4 detectors and Bob's timestamp unit. We have run communication, quantum key distribution. It worked perfectly. We noticed all the statistics those Alice and Bob collect and display during the quantum key distribution, such as coincidence rate, for detector clicking rate, quantum bit error rate, and key generation rate. We noted those statistics. Then we went to a strategically chosen location and cut the fiber. Well, actually not cut it. There was a connector strategically placed there just for convenience. Of course, you can cut the fiber, connectorize always. And then in this location, we inserted Eve in between Alice and Bob. We aligned Eve, then restarted the whole communication, and Alice and Bob ran quantum key distribution again. We monitored and recorded the values of the parameters that Alice and Bob monitor, and their statistics was just, the parameters they monitor were just the same as before the attack. They ran perfect quantum key distribution, even though now there was Eve in between running an intercept-resent attack and having the complete copy of the key. Let's look at Eve in a bit more detail. This is complete, installed, and actually running eavesdropper for a quantum key distribution system. This is fiber line from Alice coming to it, and this is fiber line going out to Bob. This black blob is Eve's copy of Bob's polarization analyzer. So this is Eve's copy of Bob. The rest of the suitcase is the faked state generator. It contains, you can maybe make out 1 laser, and which provides background illumination, and the 4 lasers which form differently polarized pulse. Then the rest are polarization controllers, fiber couplers, and some other components which are needed to form the faked state properly. This unit, and this unit are the control electronics, the delay generator for the faked state generator. Then also in Eve, we detect her detected clicks on a timestamp unit. This thing is a rubidium clock for the timestamp unit. And the clicks recorded on a timestamp unit are stored on the OLPE PC. In addition to this quantum eavesdropping setup, we also record all classical communication between Alice and Bob, which occurs over internet. Because then Eve can do the same sifting, error correction, and privacy implication procedures, and finally get the same secret key as Alice and Bob. In this combination of two eavesdropping points, well, this is really an easy part. It just takes a couple hours to set up. And this is the hard part, which takes half a year to build. This combination provides Eve with complete knowledge of the secret cryptographic key. We have this setup on display in the bike shed. Please come and see. And it's actually partly running. And to do a final check, we actually succeeded in this experiment. We check and see at a small time cut of the time diagram of clicks in Eve's 4 detectors recorded. Say, let's look at 10 milliseconds of this data. You see that there is a sequence of clicks recorded on each detectors, all in different times. Then we look at the data recorded by Bob over the same 10 millisecond period. Well, this looks similar to me. Can you find any difference between the two? I will superimpose them together. I see that there is very good correlation. So whenever Eve has click, Bob also has click. The blue and red dots superimpose. But if you already spotted it, there is a single lone dot where Eve had click, but not Bob had click. This sometimes occurs, so our control is not completely perfect. Actually, we only can cause a click in Bob with 97% probability. And sometimes Eve sends a fake state, but Bob does not get a click. But this is completely not a problem, because after transmission, Bob always reveals which click he actually had, the timing of those clicks. And then Eve just throws away those clicks which she failed to induce on Bob. So it's not a problem. And such a small deviation from unit probability of inducing a click is trivial to hide. So actually the attack works. And we are sure we have 100% information of the secure key. Now I pass to Ilya Gerhardt to make conclusions.
Oh, to make conclusions, my goodness. Okay, I saw just 10 minutes. So I'm not about to conclude yet. I think a little bit stuff I still have left. Okay, let's look for a workaround. Because let's say over there in the bike shed and also the last couple of days when we were presenting the stuff on another conference, there's always the question, hey, what are we doing? Because everything is secure on paper. Isn't there a workaround? This is just an imperfect detector. Yeah, okay. I think the biggest point, of course, there will be a workaround. Yes, there will be a nice photo detector, and the photo detector will tell you, okay, I'm blinded and I do not detect single photons. It's just bright pulse. But I think the important point here is really to realize that the security measure, by saying, well, we have this joint quantum state, we measure a click here and a click there, and later on we know, okay, this was a quantum state. This is not a security measure at all. So there's nothing super special about quantum cryptography. So we are kind of back to normal. And I think this experiment really proves it that in any case there will be implementation flaws. So of course you cannot only think about just freaking out such a QKD quantum key distribution setup. You can also fake another thing. You can fake a complete EPR source, Einstein, Podolsky, and Rosen, this entanglement thingy. You can think about other experiments. So yesterday in the night at 4 o'clock, preparing this talk, we were talking about maybe to fake teleportation or whatever. But this is not really something which I would want to talk about. But again, the laws of physics that tell you, okay, if you have a quantum correlation which cannot be explained classically, does not mean that there is no eavesdropper. So a single click in a detector is, let's say, what I expect for a single photon. But in fact, if you look a little bit on the definition, or let's say people, let's say for 100 years of a photon, they've wrote down, hey, what is a photon? My goodness. So, and I think it was a pretty smart definition by Anton Zeilinger. This is a guy from Vienna. And he just wrote down, okay, a single photon or a photon is a single click on a detector. Yeah, but let's say if I look to this stack, I think a single photon is not a click on a detector. It might be that a single photon launches a single click on a detector, but it's not the proof. So, and I think another thing is really very important. So if you, for example, click on the online shop button, buy the 100,000 euro unit, and it says, okay, we are all quantum, and that's state-of-the-art technology. Hey, forget it. You cannot delegate security. You cannot just buy a black box, think it's secure. Don't trust anything which is in a black box, first of all. I think this is really, I think this is anything in crypto anyway. So let's summarize what we did. So I think this is the first experimental implementation of a quantum key distribution setup with an eavesdropper, where the eavesdropper really get 100% of the key. And let's say 5 weeks ago, let's say working day and night, we were realizing this 290 meters, 4 buildings, kind of really under pretty realistic conditions. This afternoon, I told everybody to show up at the talk and to ask nasty questions. And I think we're about there for nasty questions. I think we have 5 minutes or something like this. So please, I think you can steal the microphone and come up with questions. Thank you.
It's quite intriguing what you presented here, I must say. The thing what was in my mind all the time, at the end you gave that away, say, well, okay, how you're gonna, the detection is not a problem if the Bob knows that he's been detected, right? So if Bob knows that somebody was listening, we throw away all communication. Okay, so I was waiting for the answer to the question, okay, Bob is looking to his voltage on his detector, and he knows he's been blinded. So, okay, then you said, okay, this is not a problem you can work around. But in my opinion, when the number of flaws in the design is sufficiently small, they renormalize to 0. And when there's too many, they renormalize to infinity. Now the question is, have you looked at other, say, flaws in the detectors or in the design or whatever, so you can give an estimate of how many of these kinds of things are to be expected? Because if their number is small, I would say that the perfect crypto system is still within reach.
In avalanche photodiode-based detectors, we know about 3 different types of flaws, each exploitable. And this is a question of technology. Build a secure detector, let us borrow it to our lab, and we try to crack it. If we fail in a year, it's fine, but nobody has built it so far. That's the problem. Surely people will make secure components, but it's not here yet, I think. I haven't seen one.
More questions. I think I can tomorrow. I make an especially explanation for more nasty questions. Over there, someone waving. I see it.
Okay, maybe that's not a question, but more comment to the last question, because I was today at the lockpicking workshop, and they were talking that it is possible to have the very secure lock with added more special keys and very precise pins and so on, but it is very expensive, and not everyone will want to pay thousands of euros per lock to protect your house. So in case of communications, especially as you said in black box communications, I am not sure whether my shop I pay with my credit card is using these very secure, very reliable detectors that are able to detect whether they are blinded or not, or the owner of the shop just went and bought the cheapest quantum cryptography system, which can be which can be blinded very easily. So that's all, I think.
Let's say, of course, you have to still realize this big selling point of QKD, quantum key distribution, is that it's kind of maximally secure. So, but I think this is, I think also a classical crypto system can do quite a good job. So, more questions? I'm a little bit blinded by the bright light over there.
Security, quantum security?
Let's say I think if we kind of melt down this whole QKD system, which we were pretty convinced in, I don't see a security proof on the horizon where I say, well, the theoreticians who write down the equations, who say this is maximally secure, that they really agree to the experimentalists making a nasty attack. I think we are kind of back to classical. I think that's about it. On quantum computation, I think this has not necessarily an outcome because, in principle, you can think further. But Vadim wanted to add something.
Yes, I can add that I personally think that the fact that people are looking for loopholes and trying to crack the systems is the maturity of quantum cryptography. Because this is a natural stage in all secure communication. You try to break implementations, you find loopholes, and then as things improve in several iterations, it becomes harder and harder to crack. This is what we hope will happen to quantum cryptography. People will start making solutions, start making protection, and then in some years maybe we fail to find a single crack in a QKD system. Then things become fine.
Okay, anyway, I think we are kind of approaching 9 o'clock. And I think I invite everybody of you to show up in the bike shed tomorrow. I think hopefully I'm still able to explain the whole shit over there. So we have all the gear over there, all the funny OLPCs we control the units with. Thank you so much, and see you tomorrow in the bike shed.
You can come now. They are there now.